can help with this? Do we know what it's projected?
It's working now, it's slow, I guess so. That's the first time I see it.
Sometimes people change their resolution or something.
But it was working before.
It was working before, yes.
It was working before, yeah.
I think it's saying you.
So I'd like to talk to you about some experiments that I've been doing in collaboration with some people at Delft and some people here in Oxford. So it's a collaboration between myself in materials, Owen Maroney, who's in the philosophy faculty, John Walton and Andrew Briggs, who are materials people in Oxford, and Lucia Ledo, Ron Hansen, and Mark in Delft. So basically, I have to explain the outline of the talk, which is an introduction to a quantum experiment called the three-box paradox, and then discuss how we've actually carried out this work, and then what we can learn from it. So, the three-box paradox is a puzzle that contrasts macrorealism against quantum mechanics. So, the basic idea is that if you have two contrasting theories of a particular system, and you want to know, is this system quantum mechanical or is it obeying classical mechanics? How can you tell the difference? And there's a method put forward for doing this by Ronald and Fagan some time ago now, so we've been trying to carry this out. So, what is, I mean, many people know quantum mechanics, but what do we mean by macrorealism? So, it contains two assumptions. Basically, if something's macroreal, it's got a definite state at any one time. So, if the cat's alive or it's dead, it's in a certain position, it has a certain speed, or it has a certain angle of rotation, etc. And if a macroscopic object's got more than one possible state, at any one time it will have only one of these possible states it could have. And the other assumption you need is that it's possible to measure something without disturbing it. So I can measure the position of an object and it doesn't respond to that measurement. So if I have these two abilities to describe a system as you typically do in classical mechanics, you can have a phase space for the position of momentum, and you can say that there's a history for the object that you're studying. So it had a particular trajectory through your experiment, or it had certain properties at certain times. Now, if you want to test for macrorealism, you can come up with an argument saying, well, the set of results I've got is inconsistent with those two previous propositions. So, Tony Leggett suggested this in the 90s. Basically says you take an operator and you give it two eigenvalues, +1 and -1, and they partition the possible states of that system. So it's like a true-false property. So like my cat's dead or my cat's alive, or my spin's up or my spin's down, etc. So once I've got this operator, I can say I'll measure it at 3 different times, and I'll look at the correlation between these 3 measurements. So I can think of it as 3 parity checks. So my Q value will either be always +1, -1. So I can say I'll look at Q1, Q2, Q1, Q3, and Q2, Q3. And in any group of 3 parity checks, only 2 can be negative. So I can just write out some combinations. I can see that either they're all positive, they're all negative, in which case the product's all positive, so I'll find a score of 3. And at most, if I pick any other combination, I'll get a value of -1. So basically, if I take the sum of these values, then I get to find a number that is always between -1 plus 3 for any system that I care to look at, provided it actually is macroreal. So then, how can you actually get a contradiction? Well, if you want to find something which is outside -1 plus 3, you have to evaluate them pairwise and assume that there is. So I mean, if I were to measure Q1, Q2, Q3, then I would always get +1, -1 for my various measurements, and I would always find a k value between -1 and +3. So then if I want to actually find a discrepancy from this, I might measure 1 and 2, and then 2 and 3, and then 1 and 3, and see whether the act of measuring the first 2 has changed the value of the one I didn't measure in between my different runs. So basically, if I do a measurement and there's a disturbance from my measurement, then I'll get the value that I didn't measure changing with respect to the times I have looked at it. And I'll detect this by finding this k value outside of the range, -1 plus 3. So I think Sam and Benjamin discussed this yesterday. We'll touch on it. So the other way you can do it is you can say, well, actually, I'm going to measure all 3 of Q1, Q1, Q2, Q3, and I'm going to use counterfactual inferences to try and deduce the value of one of these values of Q. So I could have a measurement which says, okay, Q is definitely +1 and it signals some outcome, or there's no signal, and then if I have a macrorealist reasoning, I can say, well, then I can infer that Q was -1. So what do I mean by counterfactual inference? So I think it's a reasoning that's acceptable if you make a macrorealist assumptions, but it's reasoning that you can reject if quantum mechanics is true. So my object obeys classical mechanics, I can make this counterfactual inference. If it's quantum mechanical, that reasoning is invalid. So I can apply the reasoning that is valid if the system is macroscopic, and then if I get a contradiction, I can infer the system wasn't macroscopic. So a nice example of this is zero photon imaging, which is an experiment done some time ago by Quate. So the basic idea is, suppose I have a photon going through two polarizing beam splitters that are right, so I know that my photon can never go through both beam splitters. If I put an object in the path of the light that rotates the polarization, I can get a photon coming through my dark core, basically. So now, if I have a way of blocking one of the two paths, I can have the fact that I've projected out the rotated component of the polarization, allowing the photon through the device. So I can have a detector that clicks when the photon hasn't interacted with my object, but nevertheless, the fact that the polarization has not been rotated tells me the object was there. So this is an example of a paradox whereby you see something that tells you an object is there without actually interacting with it in a macroscopic sense. So you'd expect the light to either be absorbed by the object or to have no change. So this is an example of what I could mean by counterfactual inference compared to quantum mechanics and classical mechanics or things. So if this parity check sum is violated, there's two reasons why this could occur. One is state definiteness is invalid, and the other is that there's a disturbance caused by quantum mechanics that's missing in the classical picture. And in fact, I'm going to assert that most of the experiments that have been done looking at this question fall in the second category. They're saying, well, I put something in the way of my beam of light, and therefore I get a change in my outcome, even though I would have thought, using classical reasoning, the fact that the object was there and the photon didn't hit it should change nothing later on. So it looks like there's some sort of spooky disturbance from blocking one event here that pops out with quantum mechanics at the other end. So we want to show that state definiteness can also be false, and it's not just some property of disturbance. So basically we're looking for an example where there's no detectable disturbance if you're inside the macrorealist's reasoning, but there is a disturbance inside quantum mechanics. So Bateman and Aronoff put forward a game. So basically you take 3 boxes, 2 contestants and an object you're going to hide in the boxes. And you say one of the contestants is going to evaluate the problem assuming quantum mechanics is true, and the other contestant is going to evaluate it assuming macrorealism is true, and they're going to make some contradictory predictions. And so if they actually wanted to bet on whether this system is going to be classical or quantum mechanical, they could each play this game, and the winner would determine who was right about the system they were looking at. So the game's got some rules. Basically, you have these 3 boxes, so there are 3 measurements you can do, and they're Leggett-Garg style yes and no measurements. So Alice is allowed to ask question 3, and Bob is allowed to ask question 1 or 2. And under macrorealism, these 3 questions are assumed to be mutually exclusive. So only one of Q1, Q2, Q3 can be true. Sorry, only one of M1, M2, and M3 can be true in one time. So it's as if I had a ball and I hide it in one of 3 boxes, and I can open a box and it's in there, it's not in the other 2. So that's the reasoning that Bob is going to use to get to his contradiction. So Alice tells Bob, well, I'll place this ball in box 3, and I'll shuffle the boxes around, and you can then open box 1 or box 2, but not both. And I'm not going to see what you do. I'm not going to check which box of 1 or 2 you open. I'm not going to monitor what you found when you did your measurements. However, I'll then shuffle the boxes a second time, and I'll look in box 3, and I'll use that measurement to tell you what you saw. And Alice bets with Bob, I can predict what you saw, either you found the ball or not. I can get this right more than half the time. So now Bob, thinking in terms of macrorealism, approaches this and says, well, could Alice actually win this game? Could she get my answers right over half the time? And not by playing within the rules, because Alice could always put it in box 3, move box 3 to box 1, Bob could open box 1 or box 2 at random, and then Alice would have no more than 50% chance of guessing. I mean, she'd basically have to guess because she's got no way of telling what she does. Could Alice cheat? Yes, if she put 2 balls in, or if when Bob did a measurement there was some sort of disturbance, etc., etc. But Bob can try to check whether the game is actually fair by just opening more and more boxes in some rounds, etc., etc. So Bob thinks, well, if Macrorealism is true, I should be able to win this game, and I should be able to feast Alice. Now, Alice thinks, sorry, well, the box is a quantum mechanical. I prepared the ball in box number 3, and then I set up this state, which is a superposition of each of the boxes. And when Bob opens the box, if he finds it, he's going to collapse all the coherences, and if he finds nothing, he's going to leave a coherence between the two and look inside. So, suppose Bob picks box 1. So, yeah, if Bob finds the prize he's prepared to take 1, for instance, if he has not found it, he's prepared this superposition still. And so he's basically doing 2 projectors, either he's projecting on state J or the complementary state. Then Alice measures along this final state, which has a sign change on the 3rd box. And it turns out when you look at the overlaps of these states, if Bob's box is empty, Alice will always find 0 because there's 2 components now. 1 plus 3 is equivalent to 1 minus 3, 2 plus 3 is equivalent to 2 minus 3, etc. So Alice can never find state F when Bob has not found the object. And conversely, Alice has got a 1 in 3 chance of finding state F when Bob has also seen his measurements. So, and this is also true for both boxes 1 and 2. So the only way that Alice can see F is if Bob has formed a PJ projection. So basically, in practice what we do is we use an NV center. So the nitrogen atom, weight 14 isotope nitrogen has 3 spin levels. So it has 3 levels that you can say, well, okay, the population level 1 maps into population box 1, population level 2 is population box 2, etc. So we use a solid immersion lens, which is effectively an iron beam milled structure in the surface of a diamond, which focuses on one particular nitrogen vacancy center in the crystal. So on the left you can see a sort of scanning electron microscope image of one of these lenses, and on the right you can see a fluorescing single NV center. So in the diamond crystal structure we've got basically 1 missing carbon atom, 1 nitrogen atom, and a 9-level system there. So we've gone and done this extra experiment, and we've used 1200 rounds per configuration of box 1, etc. And we expect that's going to win because this system probably is complicated. Alright, so the actual experiments is based on the work of a number of groups. I've got Wachtrup, who's speaking here, Terry Ulrich, and also Hansen. So basically the point is you have this quantum system in which, according to the modulus of the electron spin, you get fluorescences at 2 different wavelengths. So in our representation of this, we've got a group of 3 states which corresponds to the orientation of the nuclear spin with respect to a crystal axis. And then we have another group of 3 states that correspond to the electron spin. And when you examine the system, you find that this group of 6 states fluoresce at 1 wavelength, and the second group of 3 states fluoresce at a different wavelength. So you can move, you can set up coherences between these different states using microwave and RF pulses, and then you can see what you've done by asking whether the system will fluoresce under one of the other wavelengths. And so we can say, well, if this nitrogen atom were classical, we can map each of the different box configurations to each of the levels. So then, when you actually do this experiment, you can pick out the 3 nuclear spin orientations in terms of fluorescence. So we've actually got 9 levels. We're going to use 3 to represent the game, 3 to do the readout, and we've got another 3 that we don't need in this particular system. When you tune the wavelength of your laser, you can go through 2 resonances. So this EX resonance corresponds to the 6 fluorescences, and the A1 corresponds to the 3. So that's giving us our projected readout of the system. And when you do this, you find that if the electron is in one of these levels that you're addressing, you get a very bright fluorescence. So on average, you'll get about 10 photons in, I think it's about 20 microsecond measurement. And if the electron's not there, you'll get a dark. So you basically count no photons. So you have a pretty good way of distinguishing, okay, the system's there or it's not, when you're asking this question. So when we're saying on the NV center, when Bob asks, is the system in state 1, he'll apply a microwave pulse that moves from this level to this level, and he'll measure this fluorescence and see whether the center is bright enough, and so on for M2 and M3. So you can think about this a bit, and you can come up with a pulse sequence that actually implements this whole measurement. So you use the various spin selection rules to prepare an initial state, and then you've got 3 times at which this is Alice checking that the system is in state 3, this is Bob performing his measurement according to which spin level he's moved down to ms is 0, and then this is Alice again measuring whether the spin returns to state 3. So given that sequence of measurements, we can try to compare it to the macrorealist theory. So returning to the Leggett-Garg inequality, we've got 3 measurements, and we want to calculate whether this equality is violated or not. So we can take the Alice's preparation of an initial state as our first Q measurement, Bob's choice in the game as the second Q measurement, and then Alice's third measurement of the contents of the third box as the final Q measurement in this Leggett-Garg function. So if you write out, well, we're always going to prepare the state, so the first measurement is always 1. And then Bob is going to score -1 if he finds the spin, and he's going to score +1 if he can ferrets in the state he didn't look at. Then Alice is going to score +1 if she finds the fluorescence, and -1 if she doesn't. So then there's basically 6 different ways the experiment can go, and they acquire scores between -1 and +3. So in particular, Bob has to use counterfactual reasoning to work out what is the population in box 3. He can't actually, in the rules of the game, look in box 3, so he has to make an inference there, which is how we reach our contradiction. So you can think, well, there's, for instance, here's 4 paths through the system. So if the ball is always in the right-hand box, it'll score +3, and if it ever moves out of the right-hand box, it'll score -1. And you can write down the probability by summing over rows in this table, and you find there's, so I've written a tilde here for cases where Bob has to make this counterfactual reasoning. So now, if you assume macrorealism is true, then Bob never looks in box 3. He has to use these counterfactual inferences, and he goes back to his assumptions of macrorealism. He says, well, the system's always in a definite state, so I know if I were to look somewhere, I'd find something. So I can say the sum of twiddled M1 to M3 is 1. And I can also say, my measurements don't disturb the system, so if I look in box 1, if I actually do the measurements, it would be the same as if I had done the measurements. So then I can rearrange this expression that I'm trying to look for in terms of these two, which I am, by combining these two. So I can basically say, well, the chance that Bob saw it and Alice saw it is 1 minus the case where Bob measured M1 and they both saw it, and Bob measured M2 and they both saw it. So then you can derive an expression inside these two assumptions for Bob's probability of finding an object in box 3. So then it simplifies and we get this expression in terms of quantities we can actually measure on the system. So then when we actually do this, will Bob play? So now this is actual experimental data where we've carried out the game. So Bob checks that the state I is fair. So he measures these 3 probabilities and finds that there's basically a 1/3 chance of each outcome. Then he checks that his measurements are repeatable. So if he's found not M2 in the first case, you should expect also to find not M2. So if he reads M2 and he finds it's dark, you should also expect to find it dark when he tries it a few tens of microseconds later. And likewise, if he reads M2 and it's bright, you should find it bright again. So we find that in both cases we're relatively consistent. So there's a small chance that some flip will occur inside the experiment of about 5%, and in this case it was about 70% consistent. So then when we improve it and we run through all of the combinations, we find that in all cases we can get better than 80% consistency between 2 subsequent measurements. And quite a small probability for the spin to flip, and some probability here, which is basically when the electron spin ends up flipping to ns as 1. So we put the populations when we can't see it. So then, when Bob plays the game, he also wants to know, well, I'm going to assume macrorealism is true, so I want to know, can Alice detect what I'm doing? So if Alice says, well, you know, about a ninth of the time I'm finding my spin in state M3. Now, if Bob chooses between the different measurements he could do in this experiment, he could say, well, I'll do M1 and do you see a change, or I'll do M2, do you see a change, or I'll do nothing at all, can you see something going on? So if you put the numbers in to the theory, you'd find that Alice is completely blind to Bob's actions. And in fact, when we do the experiments, so we have a control of a sufficient high quality that this is almost true. So we have slightly higher probability of Alice finding M3 than we'd expect just from putting numbers in, but Alice is basically blind to either M1 or M2, and there's only a slight increase when Bob does nothing at all. So Bob would probably accept to play this game if he just could press M1, M2, or not press anything and look at Alice's measurements. However, when they correlate the results, Bob finds that Alice wins over 2/3 of the time. So under macrorealism, these two events, M1 and M2, would be independent, would be mutually exclusive. So then the sum of probability of M1, probability of M2 would have to be less than 1 or equal to it. But under quantum mechanics, it can be less than or equal to 2. So then we find that Alice is able to beat Bob about 2/3 of the time. When we put the numbers into this, we have this K value which is outside the range that's acceptable for macrorealism. So we can say quite conclusively that a nitrogen atom isn't a macroscopic object, which may not be a surprise, but we can also say, well, we're consistent with quantum mechanics, so you say, well, here are my values of Q2 and Q3 and what they would imply. Any point inside this square could be a macroscopic history. Our data is on this blue line, and it's away from the macroscopic case within errors. And also, there's no clue from within inside a macroscopic picture as to where the fault lies. I mean, you can't say that there's a disturbance caused by a measurement, which is then somehow changing the statistics. It's just simply that there isn't a history. There isn't a way of assigning the state to the system during this experiment. So in that sense, I think it's a new result in this area of Leggett-Garg tests. So then, yes, to summarise, we've got a methodology to look for macrorealism versus quantum mechanics using fully projected measurements. And in principle, this scales up to larger numbers of output measurements. So you can define this 3-box problem with n boxes and so on. So yes, so I think that basically concludes that part of the talk. So I have a few slides on some preliminary results on the Pusey, Barrett, Rudolph paper as well, which I can briefly go through. So I think we've had Barrett talking about this as well. But so what's an epistemic theory? Well, so does a quantum state represent a state of a physical state like an ontic state, or is it a state of knowledge about a quantum system? So the optic picture is that the wave function and possibly some extra hidden variables define the state you're looking at. And the epistemic picture is saying, well, the wave function might be overcomplete. Really, you need well, when you think you've prepared a state, sometimes the preparation isn't unique. So, but then you can say, well, if a wave function actually describes our state of knowledge, how can we understand? Well, so okay, the reason in favour, I think, of an epistemic theory is that if a wave function, well, if you want to understand why a wave function collapses, you can say, well, I've gained new knowledge about my system, and therefore it's just a sort of Bayesian update. But the counterpoint to that is obviously it's quite difficult to understand how the lack of knowledge about the system allows interference to take place. But in any case, it's been put forward that, or one way of looking at this is to say that when you prepare a state psi, actually what you're doing is preparing a probability distribution over some hidden lambdas. And when you have, in particular, if you have a maximally psi epistemic theory, then the full overlap between two states A and B is caused by the shared hidden variables between states A and state B. So this is trying to represent this in a picture form. So like if I have on a block sphere two orthogonal states, 0 and 1, then naught and 1 correspond to completely independent preparations. If I have two states that overlap in a small degree, so say naught and plus, then they might, when I prepare naught, I might actually prepare a variable lambda, and then when I measure the overlap of naught and plus, I'm actually sometimes preparing a state that could be either producing a plus output or producing a naught output when I measure it. So the point is that if this picture is true, then it's sometimes ambiguous as to what state we've actually prepared. So then, back in Rudolph and Pusey put forward these 4 input states and 4 output states that have the property that when I prepare this input, I never receive that output, and so on when I measure them against each other. So basically, when I measure this against this, I find nothing. When I measure this against this, I find nothing. However, together these are resolution of the identity, so I'll always get an output when I measure those 4. Then, so I can say, well, here's, if I represent my input states on a density matrix, I can see these are factorizable, and when I project input state 1 onto output state 1, I'll find these zeros, and I'll find some populations and coherences. If I try to think about how the same story would come across in the epistemic picture, then I can say, well, if I prepare the product state naught, I'm preparing a lambda for my first particle and a lambda for my second particle, which will be in this region here in some sense. Then if I look at all 4 of these, basically I'm saying, well, my lambda is somewhere amongst these 4 squares. And then Barrett and Rudolph's point is that some of the time this is indeterminate. So lambdas which are prepared in the right-hand square could be in any of the 4 input states. But when I look at the output states in the same way, I can say, well, which areas in this lambda 1, lambda 2 space have got support inside those measurements? And I can see that when I compare them, well, if I just simply write out, well, this is the area that can respond to 0 tens of 1, this is 1 tens of 0, etc. And I try to look at the combinations between them. And I find that these 4 measurement states in the epistemic case are missing the area that is ambiguous in the preparation. So when I sort of put these side by side, I can see that, again, this input never triggers that output, this input never triggers this output, and so on. However, they're missing some of the data. So I should expect to find any time I've got this ambiguous preparation, my detector's silent. It doesn't actually tell me any answer to my measurements. So you could think to yourself, well, maybe it's a question about mathematics. Is it possible to represent quantum mechanics by this sort of statistical theory? And then you could say, well, would you ever actually know the difference? I mean, I suspect, because these are actually entangled measurements, no one has ever actually been able to, if this was true, I'm not sort of saying it is or it is not, but if it were true, I don't think anybody today would be able to actually do the measurement with enough precision to tell one from the other. I mean, so like, suppose I have a measurement which measures an entangled basis with an efficiency of 30%, and this Q-squared area in the most extreme case is a 16th of the data. Am I ever actually going to know that I have a detector with like 36% efficiency and 6% of the time doesn't click because of this epistemic theory? So, in that sense, I find it quite interesting. And so, is it possible to actually tell what's going on? If we were to say, well, we have money from the Johnson Foundation to look at these kind of questions, is it possible to find a way of doing these very high precision measurements and preparations? Can we actually do this in the lab? How would we go about doing it? Then you can think, well, this is the initial state they propose. If I rotate this by 45 degrees, I can find 2 states in which the different preparations now just correspond to different phases of RF pulses in an MRI experiment. So I can prepare, say, 2 states with the same difference in overlap as proposed, just simply by switching the sign of my RF pulses. And I can take the circuit and map it onto a 4-level spin system, which is phosphorus step silicon, and I can come up with a pulse sequence that will I can find a series of different phases on the first few pulses, and then I find a constant pulse sequence that will map these 4 inputs onto the populations in 4 levels, and I can try to actually look at these overlaps and just really see what happens when you do this measurement in the interval basis. So one thing that matters is, can you actually do the rotations accurate enough? So we've been looking at resonator designs that will make the spread in rotation angle across the sample within the required bounds. So we obviously can't have more than Q squared error anywhere in the procedure. So we have a pulse sequence which keeps the errors below this breakpoint here where our total errors come above the region we call Q squared. And we think, actually in the lab we've done the measurements and we're about at 10% along the bottom axis. So our pulse sequence is insensitive to first order of any error that we might expect to encounter. And then can we actually get the preparation, we do the readouts, and how do you actually do this? So the NV center is one of the few systems which can do projected readouts on an ensemble or on an individual spin. There's a nice result which is being worked on in Salman Fraser University at the moment, which is looking at photoexcitation of phosphorus atoms. So if we take phosphorus step silicon, it's obviously a spin half electron coupled to spin half nucleus, and it has an excited state which is bound, but well, it's metastable. So if I expose it to laser light, it will go into this excited state. It will survive about a microsecond and then decay by Auger emission. So effectively, I've got 4 spin states in the ground state, so spin up electrons, spin up nucleus, and so on. And then I have an excited state, which corresponds to one hole with J's 3 halves, and the 2 electrons are now in a singlet. So basically, I have 12 optical absorptions, and every time the sample absorbs one of these photons, it then emits an electron, so its conductivity changes. And I can sweep a tunable laser through this spectra and start picking out these different transitions. So this is an idea that's been around. I think Mike Keywalt actually first proposed it in his thesis, so I found this drawing from 76 of what we should find. And it's interesting that only now, only the last couple of years, the samples have become available, because it turns out these holes are actually sensitive to isotopic effects. So the presence of different silicon isotopes broadens these optical transitions. So basically, having pure silicon 28 allows you to make these spin resolved measurements on an ensemble, whereas with the NV center, we've got a disordered ensemble, but we can pick out one member of it, so we don't care about what the disorder is. We can just sort of say, well, there's this sort of hundreds of gigahertz wide disorder, but we've got one example that we can measure. So then we've been looking at this laser cooling experiment in the CSER lab in Oxford, along with Hannah's in the audience. And basically we can start to do this state preparation with the facilities here. So we can measure the spin population, say at 4 Kelvin, so helium-4. And as we change the laser wavelength, we start depleting the ground state of the excited state and changing the spin echo intensity. And we can take the cases where we increase the polarization and turn it into an effective temperature. So we can see that by sweeping this laser across the lines, we're cooling our sample from sort of liquid helium temperatures down to below a Kelvin, just by photoexcitation, which is quite a nice capability to have if you consider that this is basically just turning the light on versus having a dilution fridge. So that's the state of play with that work at the moment. So I think we probably should be able to do the full Pusey-Barrett experiment in the next couple of months. I don't think there are any real hurdles there. It's really just the electrical measurement that needs to be implemented. So well, I guess with that, I thank you for your attention and look forward to any questions.
Any questions?
You showed the picture of the SIM.
Yeah.
Do you, I mean, I know that there were issues with the impurities if you engrave the SIM.
Yeah.
So you solved the problem, or?
This is with collaboration with the Hansen Group. So basically, we've been visiting their labs to use their setup. So I think, I mean, this really represents the work of Monsieur Leto and his student Hannah's. So I mean, this is really a collaboration. So the optical measurements have been done in Delft and in the Hansen Group. We've been thinking about pulse signals and doing the data analysis.
And there's no further questions, so we thank the speaker again. And
Q was just there now.
What do I do?
Boss. He's probably back in a minute. Yeah.
Okay, we were to. Okay.
Yeah.